15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
Hello, and thank you for joining us. Welcome. This is Space Nuts, episode 282. So good to have your company once again. My name is Andrew Dunkley. I'm your host. And this week, we're going to be looking at a new iron planet. It's a planet in a hurry, this thing, and it is orbiting a dwarf star, I believe. Quite a discovery. And of course, being made of iron, there's only one person who could possibly live there, and that's Iron Man. We will also be looking at the discovery of a new kind of binary star. Now, this is an interesting story in that up until now, it's been theory. But now, what they thought existed turns out to exist. So that's quite wonderful. So we'll talk about that. And we've got questions about a deep space probe. Not the one that your doctor is talking about giving you, but a deep space probe, and a question about angular momentum. So I've already got my ibuprofen to deal with the headache that's going to cause. All coming up on Space Nuts today. Joining me, as always, is his good self, Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Hello. Good to see you again, old chap.
Good to see you too. How have you been?
All right, thanks. Yep. A few things going on, but we're okay here.
Well, it's better than having nothing going on.
Yes.
One thing I cannot stand is boredom. I'm one of these people that's really fidgety, and I need something to do all the time. And you know, people say to me, why don't you just have a rest and have a bit of a snooze in the afternoon? No way. I hate wasting daylight. Sleeping you can do at night. Well, no, I don't do that very well either. Now, Fred, we've got a lot to talk about. So let's move on to our very first topic about this little planet made of pure iron, and it is moving at a rate of knots.
Yep, its name is GJ367B, and it's in the constellation of Vela, which is a Southern Hemisphere constellation, which is very prominent in our skies here in Australia. So what we're talking about here is a discovery by TESS, the Transiting Exoplanet Survey Satellite. And you'll remember, Andrew, that the way TESS discovers planets is by staring at patches of space. In fact, it's done quite a lot of the sky, staring at patches of space and looking for stars whose brightness dips very slightly to reveal a planet transiting across the disk of the star. You can't see either the planet or its transit across the disk. All you see is the light of the star diminishing by a tiny, tiny fraction usually. But our measurements these days are so precise that it's possible to determine that. So that gives you, first of all, it tells you there's a planet there when you register these dips. Second thing it tells you is how fast the planet is orbiting around its parent star. And this one, it goes around once in it's just under 8 hours, I think. So
Blimey.
That's its year. Its year is 8 hours.
So you could get very old very fast on this planet.
Yeah, that's right, indeed. Well, you might, just because it's such a peculiar place. So that tells you it's close to its parent star, which, by the way, is a red dwarf star. It's about 30 light years away. I don't know whether I mentioned that. But okay, so what you also get from the transit observations is the diameter of the planet, because you know the diameter of the star. We know star diameters pretty well, and we can tell that from their spectra and their colours, essentially. So once you know the diameter of the star, and you know kind of the details of the dip in the planet's light the star's light as the planet goes across, that actually lets you measure the essentially the diameter of the star. The diameter of the planet. I beg your pardon.
Yeah.
Should think about this, shouldn't I, before I open my mouth? But then what you do is you go and do some ground-based observations with bigger telescopes than TESS. And in fact, the instrument that was used to do the follow-up observations was one that's well known to people who study these exoplanets. Is an instrument called Harps, which stands for High Accuracy Radial Velocity Planet Searcher. It's down in Chile. It is operated by the European Southern Observatory on their 3.6 meter telescope, if I remember rightly. So that lets you, the High Accuracy Radial Velocity Planet Searcher, what that lets you do is measure the wobble of the star caused by this planet going around it. And once you've done that, you can determine the planet's mass. So what you've got is the mass and the radius of the planet, and it's all been done very precisely. The measurements are quite exquisite in their precision. But what the mass and the radius give you, of course, is the density, because the radius gives you the volume, density is mass per unit volume. And so what these scientists have established is that the density of this object is rather more than 8. Let me just get the number up, because they've got a pretty accurate. Yeah, this is in the old units of grams per cubic centimetre, which I know and love. 8.106, that is the density of this planet. And that's much more than the Earth. And significantly, Andrew, much more than Mercury, which is a highly dense planet that we think has its high density because most of it is an iron core. And the thinking is that Mercury was well on its way to being a normal planet with an iron core caused by the molten iron sinking gravitationally to its centre, and a rocky mantle. But the rocky mantle might well have been blown off in a collision with another object. That's how we think Mercury got to be the small world it is, even though it's got a giant-sized core. And the thinking now is that maybe this strange world with its 8-hour year has had the same phenomenon. We just don't know. There's not enough known about this world yet to really hypothesize. But that seems the most likely thing. To get a world that is almost pure iron, which the density is revealing, tells you that there's not much else there, and maybe that iron core formed along with a rocky mantle like we have on the Earth, but something collided with it. Probably in the early days of that solar system, knocked off the mantle, and you've got what amounts to an iron planet. Now, one of the things that is perhaps another additional piece of information about this world, which is one of the things that makes it even less hospitable than an iron world might otherwise be, is because it's close to its parent star. But it's very hot. So its temperature is probably 1,500 or so degrees Celsius. That means it's actually hot enough to melt iron. So maybe on the day side of that world, you get lakes of molten iron. Who knows? But the night side, of course, because this is one of these worlds that's tidally locked to its parent star, so it rotates in the same speed as it revolves around in the same length of time as it revolves around the star, 8 hours. That means that the dark side is permanently the dark side, and it's probably absolutely freezing on the dark side. A really, really weird sort of place. Very hard to get your head around it, but that's what these measurements tell us.
So it sounds like it's very much a larger Mercury type planet.
Yeah.
If we want to compare it to something local, do we know why it would be orbiting so fast?
No, and it's one of the interesting aspects of solar system. If I can put origin theories, is that we now see such a range of different solar systems in terms of the exoworlds. When we look at the solar systems of other stars, they come in a complete range of them, and so lots of theoretical work has been done on how you get solar systems that can look so different. And one of the things that seems likely to have happened, and probably happened in our solar system as well, is that planets over long, long periods of time actually migrate backwards and forwards within those solar systems. And, this little world that we're talking about, it orbits so fast because it's so close to its parent star. The two things are inextricably linked. The nearer you are to your parent body, the faster you orbit. It may well be that it was formed further out in that solar system. And it may also be, Andrew, that there are other planets in that solar system that we haven't yet detected. One with an 8-hour period around its world is relatively easy to detect because you don't have to observe it for very long to see these regular dips in its in the star's brightness, and you know that there's a planet going around really very rapidly. But with something maybe at the distance of Jupiter from the Earth, then you've got to wait a long time before you see progressive dips. So
didn't we discover one recently where it was like 100 years or something before it transits again? So
yes,
to actually confirm it, because you've got to get more than one transit, don't you?
Yes, that's right. I think it was it 76 years, if I remember rightly.
Yeah, so we've got to wait that long.
That's still a planet that's hypothesized, so you can't make it a certainty. But this world is. It's interesting. It's a bit of a record breaker. I don't think it has the record for the highest density exoplanet ever discovered, but it's very close to it. Yeah. But it's it is pretty extraordinary in all its in all its attributes. So very much on the cusp of being a record breaker.
Now, you say it was initially discovered by TESS. I understand the purpose of TESS is to try and find Earth-like planets, and so it's found this one. Why are we so focused on Earth-like planets? Is it because of the potential for life, or we just want to find planets that are like ours to see how many are out there?
All of the above, really. It comes about partly historically, Andrew, because the first planets that were discovered beyond the solar system, initially, there was a huge tranche of planets discovered by what's called the Doppler wobble method. And the Doppler wobble is the one that we mentioned in connection with this little planet. The way it works is that you look for the movement of a star that's induced by the planet orbiting around it. There's a wobble of the star itself. And that is basically that, slants you towards higher mass planets. So very much the planets that were discovered early on in our knowledge of exoplanets were the big ones, the Jupiter-like planets, and bigger still. And so it turned out that the Doppler wobble method is actually not a good method for discovering Earth-like planets because, or Venus planets or Mercury planets, because they don't wobble their star as much because they're less massive, they're smaller. But the transit method is good at revealing them because you can actually measure things smaller than the Earth by the transit method. So that was, one of the reasons why TESS was built, to follow up actually on the work of Kepler, which was another transiting exoplanet, the first one that did this sort of work, the first satellite that did exoplanet transit measures, and reaped a really rich harvest, which is why TESS was followed up. But yes, of course, the basis of your question is right. We're interested in Earth-like planets because we live on one. Yes. We want to know how many there are out there, and maybe whether there are others that might support life.
Yeah, it surprises me, but ours is very much like Earth.
It's extraordinary, isn't it? The resemblance is really quite striking. Yes, yeah.
I suppose something else that's come out of all of this, and you touched on it, and that is that there is no typical solar system. Yeah, it seems like they're just all so variable.
That's right. Yeah, we spent hundreds of years thinking that, well, solar systems must all be like ours, if there are any. We didn't even know whether there were any others.
Yeah.
Now we do. We know that there are, and they come in all kinds of shapes and sizes, which has stretched, it's stretched the minds of the people who build models as to how solar systems form, because you've got to try and accommodate all these different sorts of morphologies, the way, the shape of the solar systems, the way they look. Interesting.
Well, yeah,
stuff.
we've had to learn to think differently, because some circumstances are almost inexplicable. And I remember when they first discovered gas giants orbiting close to the sun, to their respective stars, people went, "How can that be?
How can that happen?" Yeah, the hot Jupiters. That's right.
It's extraordinary. Well, there'll be more to discover, and TESS is a pretty exciting project. So we will probably be talking about other things that it discovers in the not too distant future. You're listening to Space Nuts with Andrew Dunkley and Professor Fred Watson. Now let's take a little break from the show to tell you about our sponsor, NordVPN. Now, I just want to clear one thing up initially. We've had a bit of a social media post about the price of the deal. And I've done a bit of research, because a few people have thought that they were being overcharged. But the fact of the matter is that Nord advertises its prices on its website in US dollars, Great British pounds and euro. So when you're looking at the link that we're going to give you, it will be in US dollars, not Australian dollars. Therefore, there'll be a conversion. So you might have to just do the conversion to see what the Australian price will be. Of course, that fluctuates greatly, and the money market has a big effect on that. So just bear that in mind when you look at this deal. Even so, it is still an excellent deal. You are still getting a fabulous price for a quality product, and that's NordVPN. Now, NordVPN is endorsed by a lot of great organisations and websites. Even the BBC, Forbes magazine, Huffington Post, all look at Nord as the top of the tree when it comes to virtual private network security. Now, if you are worried about hackers, you don't want your bank details stolen, you don't want people looking at what you're looking at online, or you just want the security of knowing that you have got a very solid wall between you and anybody else who might want to touch your stuff or get into your systems or steal your passwords or empty your bank account, or if you just want to log on to the internet and watch something overseas that's geo-blocked, a VPN service is the way to go. You won't get anything better or faster than NordVPN. Now, as a Space Nuts listener, you do get a very special deal. For a limited time, 73% off a 2-year plan. For this holiday season deal, go to nordvpn.com/spacenuts. Use the code SpaceNuts to get up to 73% off your NordVPN plan, plus a bonus gift. There's a 30-day money-back guarantee, and it is a fabulous system that will secure your internet browsing. So go and have a look at it, nordvpn.com/spacenuts. Check it out and hit the grab the deal button to take advantage of this fabulous offer from NordVPN, our sponsor, as a Space Nuts listener. Now, back to the show.
Roger, you're loud and clear here also.
Space Nuts.
Now, I'm often banging on about people becoming patrons, which you can do via our website. Just hit the Support Space Nuts button at spacenutspodcast.com or spacenuts.io. But got some news. There's something new on our supporter page. Now, you can become a patron through Patreon or Supercast, and there are 30-day trials. If you don't like it, you can get out. And you can decide what you want to put into the kitty once a month. You can also make one-off donations through PayPal, but we've brought in something new. There's a Buy Me a Coffee link. You click on the Buy Me a Coffee link, and that's it. You're basically making a donation to the show to the value of a cup of coffee. So if you can go without coffee just once to support Space Nuts, you can do that via our supporter page, spacenutspodcast.com. Click on the Support Space Nuts link. Everything you need to know is there. And if you want to just make a one-off donation to the show, you can do that, or you can go the whole hog and become a fully fledged patron. It's totally up to you, and I'll leave it at that. Now, Fred, let's move on to our next topic. And that is, this is a really interesting story. This is about a binary star. Now, most people think of binary stars as two independent stars orbiting each other, being friendly. But there's been a kind of binary star that up until now has only existed in theory. But what's really exciting is they've now found one.
I think they found 21 of them, actually, which
21?
is... Yeah, let me...
Is that what that symbol means? That's right.
No, you're absolutely right. What they've done is found examples of this class of stars that has basically... actually, let me correct myself. It's 13 of them. But because the number keeps going down.
Joke.
We'll get down to... Sorry. But you're absolutely right. The point is that this class of stars actually exists. That's what this is all about. And that means that, yes, they have found one and more than one. So what we're talking about here, Andrew, are things called ELM or ELM, which I like rather a lot, white dwarfs, ELM white dwarfs or ELM white dwarfs. ELM stands for extremely low mass white dwarfs. And we know a lot about white dwarf stars, and we recognize whereabouts they fall in the sort of evolutionary pattern of stars, and it's pretty near the end. And in fact, the sun will eventually become a white dwarf star. When it runs out of hydrogen fuel, its atmosphere will expand, but its core will contract to this what's called state of electron degeneracy. That's how you define a white dwarf. It means that only the electrons are preventing the thing collapsing into a neutron star. So white dwarfs are typically the size of the Earth, but with the mass of a star, or a significant fraction of the mass of a star. And that's your average white dwarf. And they're very, very prolific throughout the sky. We see them everywhere, and we know how they're formed. They're ancient, normal stars. But there is this class of white dwarfs whose masses are very, very low, less than a third of the mass of the sun, in fact. And the reason why this has been a puzzle is that if you think about a white dwarf like what the sun will become, how that evolves beyond, during its white dwarf phase, if I can put it that way, beyond the normal life of the star, you've got the white dwarf formed, and then that continues to evolve, and typically they lose mass. And the conundrum has been, I'm sorry, I'm probably not making this very clear, but the conundrum has been that to get down to about a third of the mass of the sun, in other words, to being an ELM, an extremely low mass white dwarf, to do that, you need more than the age of the universe for the mass to leak away. You can't have white dwarf stars that are older than the universe because that's a bit of a problem. So one of the actually, it's a nice quote from one of the authors of this work, Karim El-Badri, who's used the big telescope at Lick Observatory, which I've visited in the past. Karim says the universe is just not old enough to make these stars by normal evolution. And so you've got to have another method. And the method that has been proposed, is that if you get a white dwarf as a member of a binary system, in other words, you've got another star, a companion star, the two are orbiting around their common center of gravity, and that is a common scenario. But in this case, the other star is near enough to the white dwarf that it can suck off material from it. It sort of eats away at the white dwarf until it becomes an ELM white dwarf. So that is what has been hypothesized. And what has now happened is that these things have actually been observed. and it's using actually data from Gaia, that fantastic European Space Agency spacecraft that's measuring the directions of stars to millionths of an arc second. And actually, there is another telescope involved as well, something called the Zwicky Transient Facility, which runs on a telescope that's actually a twin of our Schmidt telescope at Siding Spring Observatory here in Australia. So they looked for evidence of these things, and they followed up the binary systems using the Shane telescope at Lick Observatory. And to cut a long story short, they basically have identified stars that were losing mass to a companion white dwarf. The white dwarf that is losing mass to a companion star. I got it the wrong way around. So that's it's actually back to this 21 number that we started off with, and kind of 21 is right. Of that, 13 showed signs that the white dwarfs were still losing mass to the companion, but the other 8 seemed no longer to be losing mass, but they were all ELM white dwarfs. They were all extremely low mass. And they also discovered that they had higher temperatures. There's another attribute to these things. The white dwarfs had higher temperatures. So they're apparently going to follow up on these extremely low mass white dwarfs, in other words, the ones that are still losing mass, and the ELMs themselves, to really try and find out the gaps in our knowledge of how these things occur. But it's as you say, it's a great detective story with a good outcome. They've actually got a smoking gun there.
Your confusion over white dwarf and non-white dwarf stars also explains why you're so bad at snooker. Always sinking the white. But, I do have a question.
I haven't played snooker for years, but I used to play a lot, Andrew.
I read a story the other day about a UK champion. Actually, he's a former world champion who was playing in the UK championships the other day, who fell asleep during a match. Ended up losing 6-5 when he was in the lead 3-2. So
talk about being relaxed.
You know what? He blamed COVID because he was suffering extreme exhaustion as an after effect of having COVID in October.
Oh, that could be it.
Yeah, that's by the by. But I thought of a question because you said our sun is most likely going to become a white dwarf. In fact, the article I'm looking at here from phys.org, phys.org, says that our sun is 97% likely to become a white dwarf. So if it doesn't, what is the 3% chance of it becoming?
Something else.
Okay.
Look, it's not going to become a neutron star because it's not massive enough. It could, it's possible just to have something that collapses to a remnant that is not electron degenerate, which is what you have to be a white dwarf, this state of the electrons jostling together, and that's being the only thing that holds the thing together. So it may be that its core could shrink, but not to the level of being a white dwarf. It still would gradually cool down because it's got no more fuel to keep burning, and eventually would probably become what the white dwarfs eventually become, which is a black dwarf. It's a star that's stone cold, but white dwarfs last a long time. It's a long period of stellar evolution, the white dwarf phase.
Yeah, okay. Well, maybe the way our planet survives into the future is we move away when it becomes a large, nasty thing, and then when it shrinks back, we move the Earth closer. Seen it done in sci-fi. Yeah. I don't see why we can't do it for real.
Well, that's right. We've just sent a spacecraft to an asteroid to see if we can move that. So these things start small and eventually get useful.
Yes, indeed. All right. Anyway, it's a great discovery and one that certainly gives us some answers and has turned theory into reality. This is Space Nuts. Andrew Dunkley here with Fred Watson.
Space Nuts.
Now, if you're looking for something special for Christmas, do not forget the Space Nuts shop. I mean, you can get one of those. That's a tote bag hanging on my door in the back of my office. You can get the Space Nuts cup, which is also up there. Oh, there it is. It's right next to the tote bag. You can get shirts. You can get stickers. And of course, if you're a patron, which I talked about earlier, we send you presents. For the longer you're with us, the bigger and better the present gets, right up to anybody who sticks with us for 100 years gets Fred's Maserati. So it'll be an antique by then.
It'll take me 100 years to pay for it as well.
Is that all? Anyway, if you'd like to look at the Space Nuts shop, that's on our website, spacenutspodcast.com or spacenuts.io, where you can click on the shop link and see what sort of things are available. Buy something for yourself or somebody that's hard to buy for, and somebody you know loves astronomy. Fred's new book's on there as well, Space Warp, and a few other things also. So it's well worth visiting. And while you're online, jump on Facebook and Instagram and follow us. We've got an official Space Nuts Facebook page, and we now are on Instagram, and I think we're getting followers at a rate of knots. Spacenuts.io is the username on Instagram if you'd like to follow us there. Now, Fred, time for some questions. We've got audio questions today, and the first one comes from Andy.
Hi, Fred and Andrew. It's Andy here again from Melbourne. Once again, my obsession with satellites continue. My questions this time are a bit of a what-if scenario. If we were to launch a deep space probe and place it into an orbit past the Oort cloud, 1, is this possible? 2, if you had to design the mission, what areas of study would you concentrate the probe's instruments on? And 3, do you think we could learn anything different than a similar probe orbiting closer to Earth? Thanks again for the great show. P.S. Andrew, I've started to listen to the Terranean Enigma, and it's great. Classic sci-fi and very engaging. Have a good one.
Thanks, Andy. I'm glad you're enjoying it. It was fun to record, but I hurt my throat doing some of the alien voices. I really did, and some of them are a bit weird. But especially the characters known as the Borsch, they nothing to do with German food. They were an evil race that I wrote into the story, and they sounded like this, and it really hurt to try and replicate that. What I thought they sounded like. But I'm glad you're enjoying the audiobook. And I'll tell you, I've almost finished editing up the Hitler paradox. Too many nationalities in it for me to tackle in terms of accents, so I've kept it fairly simple this time, mainly for self-preservation purposes. So I'll let you know when the audio version of the Hitler paradox is out as well. What did Andy want to know? I've got no idea. Deep space probe. Deep space probe.
Actually, it was a bit hard to hear, Andy. I'm not sure quite whether the sound is coming through the normal channel there, Andrew, but I did get the gist of his question. The mission to the Oort cloud or to pass through the Oort cloud, it's a really interesting question. And in a sense, we're doing it already because Voyager will one day pass through the Oort cloud. Voyager being, there are two Voyagers, the two most distant human-made objects. Voyager 1, if I remember rightly, somewhere in the region of 21 or 22 billion kilometres away from Earth. But the Oort cloud is much, much further than that. So, we'll be passing through the Oort cloud maybe in 500 years or something like that. It is that far away. It's well on the way to the next nearest star. And the other thing about the Oort cloud is that it is very rarefied. It's not dense in terms of how there being lots and lots of objects there per cubic kilometre or whatever. And in fact, that's really the reason. It's this sort of rarefied nature of the fact that you've got icy objects which are separated by huge distances. That's really the rationale for why we think there is an Oort cloud, because you've got this region of space where the density of objects is not high enough for them to interact with one another and form planetesimals like they did in the inner solar system and go on to make protoplanets. If I can put them that way, the planetesimals, the small objects that potentially could be formed by these lumps of ice in the Oort cloud just never really happen because they're too far apart. The Oort cloud, in many ways, is a big sphere of nothingness, and so the Voyager spacecraft is well equipped to make measurements, or it would be if its batteries were still running by the time it crossed the Oort cloud, and of course it'll be way out of reception of range of our radio transmitters by then. So I suppose if you did want to explore the Oort cloud directly, it will be a spacecraft that has a very long life and very powerful radio transmitters that you're going to be able to receive signals from for a long time.
I suppose we're going to have to become more reliant on observation platforms like James Webb, which is almost due to be launched.
Yeah, that's right. So it will be terrestrial observations that tell us more about the Oort cloud. We don't think we've ever directly seen an Oort cloud object, apart from long period comets, which come into the inner solar system, and we think they're Oort cloud objects that have been disturbed out of their orbits. But observing one directly, some of the what are called ETNOs, extreme trans-Neptunian objects, some of those objects are thought, these are very, very distant icy asteroids, are thought to be possible candidates for being on the inner part of the Oort cloud, but we really don't know with any certainty.
So I'm a bit confused. We talked about Voyager recently sort of getting beyond the effect of the sun, which means it's beyond our solar system technically, or beyond the influence of the sun. I can't think of the name of that point.
It's the heliosphere.
The heliopause.
Yeah.
So and it's got so much further to travel to get to the Oort cloud.
Yes. And that your point is well made, because a lot of people get confused by this, and we often see, headlines saying Voyager has left the solar system, and what it means is that it has left the sun's magnetic influence. The magnetic the region of the sun, or the magnetic influence area of the sun, is what we call the heliosphere. And you're right, the heliopause is the edge of it. But the gravitational influence of the sun goes on much, much further than that. So when you talk about the edge of the solar system, really, it's not where Voyager is. That's still our backyard, but it is the edge of the sun's magnetic influence. So it's combined. I think you've got to separate these two. The gravitational influence, which is what holds the Oort cloud in place, is much, much greater.
So would it stand to reason that even though we don't know much about the Oort cloud or have seen any Oort cloud objects, that there would be multiple Oort clouds in multiple solar systems?
Yeah, I think you might find every solar system has its Oort cloud, if I can put it that way.
So if we can see exoplanets, why can't we see their Oort clouds?
Because the objects within it are just tiny. Their sizes are measured in handfuls of kilometres, if that, rather than planet-sized. Yeah.
I'm being very journalistic today.
Oh, you're doing well. But Andrew, as always, you are asking all the right questions.
That doesn't happen very often. Okay. Thank you, Andy. Lovely to hear from you. I'm glad you're enjoying the Turanian Enigma. Now we're heading off to New Zealand.
Hi, Andrew and Fred. This is Matthew Willey from Palmerston North in New Zealand. I'm just wanting to ask a question about dark matter and black holes. Just kidding. Just kidding. It's about angular momentum. Now, I know that the moon and the Earth are losing angular momentum, and this is because of tides. And that is making the moon move further and further away from the Earth over time. But I've got it in my head that, if we actually removed all of the angular momentum from the system, the moon would drop out of the sky and land on the Earth and make you very unpopular. So there seems to be a contradiction between no angular momentum causing the Earth and the moon to move towards each other rather quickly, and just reducing angular momentum, making the Earth and moon move further and further apart. So I'm just wondering if you could talk me through that. That would be really helpful, because it's doing my head in. Thank you very much, you guys. Love the show. Keep doing what you're doing. very much appreciated from where I am.
Yeah, well, you're in New Zealand, so that's understandable. Thank you, Matthew. Sorry. Yeah, and leave the jokes to me. Speaking of which, the real reason that the moon is moving away from us is because of Alan Shepard. Now, when he was on the moon, he hit a couple of golf balls and he hit a massive slice, and that's why the moon's spinning away from us. It's simple as that. Otherwise, it could be something else, I think, Fred.
It might be something else, yeah. So, I think, look, Matthew's question is a great one. The angular momentum itself is actually conserved. We conserve the angular momentum, and that's kind of what allows things to keep on spinning. And it's actually also what allows us, that principle of the conservation of angular momentum is what allows us to work out what the solar system was like in the distant past. Because we know that the momentum energy, the rotational energy of the Earth and Moon is essentially conserved. Now, there are tweaks on it at a much lower level, and that's where this tidal friction comes in. And so it's if you forget about the loss of angular momentum and just think that that is being conserved, then that's all good. But the tidal friction clearly has an effect, a very low level effect on it, which is temporary, I have to say, because tidal friction will eventually stop. And so the thing will keep on spinning. The moon will never ever fall to the Earth because of a loss of angular momentum. That angular momentum is there forever.
That's good news.
Let me explain why the Earth is pushing the moon away, if I can put it that way. And it comes about because of the tides. So the moon raises tides on the Earth. And we've all seen diagrams of the Earth with this strange oval bulge around it, which are the effects of the tides. And that is called the tidal bulge. And it's not just the oceans. The Earth itself does the same thing. But you'd naturally expect that tidal bulge, that oval of material, to be aligned directly with the moon, because it's the moon that's pulling it. But actually, it's not, because the Earth is rotating underneath it. So the bulge moves slightly eastwards because of the Earth's rotation. And that's where the friction comes in, because it's the friction between the oceans and the rocks of the Earth and the rotation itself that is causing that bulge to move eastwards. Now, the eastward move of the bulge has a tiny effect back on the moon because it's changing the gravitational pull of the Earth. And what it's doing is giving the moon a slight gravitational acceleration. It's pulling on the moon and increasing its velocity. And as soon as you increase the velocity of something in orbit, what it does is moves away. And so that's why the moon is drifting away. And the energy is going into the rotational energy of the Earth itself. That is that the Earth is slowing down. So that's where the energy pushing away the moon is coming from. It's coming from the Earth's rotation, not the angular momentum of the Earth-Moon system. Now, eventually I said tidal friction will stop because the ultimate end product of this scenario is that the Earth slows down so that it rotates in the same time as it revolves. Sorry, as the moon revolves around it. And you've got this situation where the Earth and the moon face one another permanently, and that will stop the tides and it will stop tidal friction. And so that scenario of the Earth and Moon facing one another, I think the period would be 43 days. The day and the month would both be 43 days. That will go on ad infinitum unless there is some external disturbance to the Earth-Moon system. And
that's due to happen next week, apparently.
Probably next week, plus maybe 15, 20, 30 billion years. Maybe.
Right.
Yeah.
And hypothetically, what would it be like to live on the planet?
Yeah, very weird.
Could we live on the planet?
Well, the thing is, it'll never happen because by then the sun's done its thing, and
of course,
become a red dwarf. Sorry,
so we don't care. It doesn't matter.
A red giant star. No, it doesn't matter because we'll have probably been absorbed into the sun's atmosphere by then anyway.
Yeah,
it's all great stuff. So
if humanity survives, we won't be here, I imagine. We'll have found another way to get away.
I think so,
somewhere else. Yeah. We'll have solved all those issues of folding space and
all of that.
Other planets to live in. I thought that question was going to give me a headache, and I had my ibuprofen ready to go, but it's actually quite a simple explanation, really. It makes absolute sense to me. So I'm guessing that the more astute amongst us have figured, of course. Yes, absolutely.
Anyway, it is a great question from Matthew, though. And I take his point, but the angular momentum is conserved. That's the bottom line.
Indeed. All right. Thanks, Matthew. Thanks for sending that in. We love these challenging questions. And thanks, Andy, and thanks to everybody who contributed. Thanks to our supporters all over, our sponsors, of course, but our listeners. I've been getting some great feedback from my terrible dad joke last week about the Earth being flat because the water's uncarbonated. That's been shared via social media and gone ballistic, and I can't claim the joke. I saw it somewhere else. Somebody else thought of it, but it's a great one to share, and I'm glad I could give it momentum. You gave
it a bit of fizz, actually. That's what you did.
I did. And thanks for the feedback. I love hearing from people, and I quite often get messages. And once again, I'll mention our social media platforms if you want to follow us there, and the Space Nuts podcast group, which is a user-created Facebook page where you can all get together and chat. Don't forget that one as well. It is well worthwhile getting together so you can share your pictures. I know Andy loves to share his pictures, his astronomical photographs online. He's done some spectacular work too, I must add. That brings us to the end. Fred, thank you so much.
Great pleasure, Andrew. As always, we'll talk again next week, I hope.
We will. And don't forget, if you want to get in touch with us, you can do that via our website through the AMA tab, spacenutspodcast.com. Click on the AMA tab and you will be able to send us an audio question or just send us a note. Some people just like to make comments. You can do that through the text interface or on our website. Thanks as always to Fred. Without him, this would be half as good. And it probably wouldn't even be that good.
Might be twice as good.
And from me, Andrew Dunkley, thanks for joining us. Looking forward to your company on yet another episode, probably next week. See you then. Bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Complete Houston.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.